Recent advances have markedly improved the cross-scene generalization of depth estimation, yet its practical applicability remains limited by the absence of metric scale and low computational efficiency. To resolve this scale ambiguity problem, a straightforward approach in previous studies leverages 3D point clouds to perform least squares optimization for global scale recovery. Nevertheless, this solution often suffers from limited precision, as local regions may exhibit scale inconsistencies. Different instances or segments exhibit distinct scale ratios, and shift bias is utilized for recovering metric depth. Another line of research investigates incorporating captured 3D data into the depth completion or metric depth estimation framework via neural networks. However, these approaches are typically trained in domain-specific environments, which limits their ability to generalize across diverse scenes. Addressing this issue requires large-scale training datasets, which in turn significantly increase the cost and complexity of data collection. To address these issues, we present Midas Touch for depth. It employs an efficient, effective, and universal paradigm for converting relative depth to metric depth. It is a mathematically interpretable approach and can handle different types of extremely sparse 3D data. It is highly practical and support various downstream 3D modeling tasks. Compared to previous method, our method can correct local inconsistencies and improve the depth quality, and requires no additional training. Specifically, our method takes relative depth sparse 3D seeds and a segment set as inputs and outputs reliable metric depth. We avoid fine-tuning the depth foundation models, thereby preventing potential performance degradation. In the overall framework, segment-wise recovery followed by pixel-wise refinement forms a coarse-to-fine pipeline. Segment-wise recovery. When converting relative depth to metric depth, the scale often varies across local regions, so a single global rescaling is insufficient. We therefore partition the image into segments. Per segment calibration first recovers scale for segments containing projected 3D seeds. A lookup table is utilized for store the parameters of the calibration function. Due to the sparsity of 3D seeds, some segments receive no seed projections and lack a reliable scale. To address this, we construct a segment graph and propagate recovered scales from seeded to unseeded segments. Pixel-wise refinement. Segment-wise recovery provides a coarse metric depth estimate, but per segment matching leaves residual pixel-level errors. We therefore introduce a mathematically interpretable, pixel-wise refinement to correct these residuals. Based on coarse depth, we derive pixel-wise discontinuities that guide the paths of depth propagation. We formulate the geodesic problem as a path integral optimization and solve it efficiently via dynamic programming, progressing from local updates to a global solution. In conclusion, to maintain interpretability and improve efficiency, we develop a reliable non-parametric method with a clear mathematical foundation. Using the above-mentioned framework, we can leverage available 3D data to efficiently and accurately convert relative depth to metric depth. Our method achieves strong accuracy and generalization, outperforming state-of-the-art approaches. Our method can be used in downstream applications such as SLAM. Our method can be employed in handheld edge devices, thanks to its low inference time and high accuracy. For commonly used range cameras, our method can also serve as a plug-and-play module to enhance the quality of low-cost depth data. Thank you for watching our video.